All right, in this video, we're going to take a look at vertical and horizontal stretches and compressions of the graph of a function. So this time we're going to look at a different function. This is the sine function from trigonometry. And for f of x equals the sine of x, determine the effects on the graph if we have g of x is a times f of x. So if we multiply our entire function by a number. Well, we know what happens if we multiply our entire function by a negative. It's going to reflect it over the x-axis. So let's see what happens if we multiply it by a positive number. If we multiply it by 0, it's just going to wipe everything out to 0. So if we multiply it by 1, it won't change anything because 1 times anything doesn't change the value. So let's start by looking at values that are bigger than 1. So here we have our sine graph, which looks like a wave. And we have 1 times our sine wave, so it's not going to change it. But if we adjust the value of 1, look at what happens to our graph. It's stretching away from the x-axis. So here's the graph of 5 times the sine of x in blue. Notice that the intercepts of the graph, of the original graph in red, the intercepts stay on the axis. And what actually happens here is we're multiplying all of our y-coordinates by this value of 5, or whatever the value happens to be. So originally we had, you don't have to worry about this 3 pi over 2 bit here, but originally we had a value of 1 for this relative maximum here. Now we have, at that same x value, a value of 5. So we just multiplied all of our all of our y coordinates by whatever this number is. So now our graph is, all those y coordinates are 5 times further away from the x-axis as they used to be. And there we go again. So it's a vertical stretch if we're multiplying by a number bigger than 1. And the value that we're multiplying by is called the factor. So it's a vertical stretch if we're multiplying our function by a number bigger than 1. And that number is called the factor. And the y-coordinates are now, whatever that value of a is, that many times further away from the x-axis. So originally this point was 1 unit away from the x-axis. But if we multiply the function by 5, now that same x-coordinate on this blue graph is 5 times further from the x-axis as it used to be. All right, now let's see what happens if instead of a number bigger than 1, it's between 0 and 1. So I keep doing that. I'm just going to adjust these values here. All right, and now let's see what happens as we multiply by a number between 0 and 1. So notice now our graph in blue is getting closer to the x-axis, so it's pressing downward on it. So here we have the graph of 1/2 sine of x in blue. So notice now, now our y-coordinates are twice as close to the x-axis as they used to be for this 1/2 times the sine of x. So here we have a vertical compression if we're multiplying our function by a number between 0 and 1. And the factor for vertical compression is going to be the reciprocal of a. And the reason why is because it measures how much further or closer we are to the x-axis. So we saw a vertical stretch is further away. Here in blue, we have a vertical compression. Now it's twice as close as it was originally. So with vertical compressions, we take the reciprocal of the number we're multiplying by, and that is our factor. So the y-coordinates are now that many times, a times closer to the x-axis. So example 4, determine the effect of the graph of f of x equals sine of x for each. We have g of x equals 12 times the sine of x. So with that one, if we do 12 times, now our function is way further away from the x-axis than it used to be. It is a vertical stretch by a factor of 12. For 1/3 sine of x, we have 1/3 is between 0 and 1. So it's a vertical compression, and the factor is the reciprocal of 1/3, which is 3. For g of x equals -80 times the sine of x, well, the negative part is a reflection across the x-axis, and then the 80 is a vertical stretch by a factor of 80. So your vertical stretches and compressions, then if there's a negative in front of them, that's a reflection across the x-axis. So your vertical stretch and compression will always be a positive factor. For negative 2/3 times the sine of x, the negative once again refers to a reflection across the x-axis. And now it's a vertical compression because 2/3 is between 0 and 1. It's a vertical compression by the reciprocal of 2/3, which is 3/2. So now your points are 3/2 or 1.5 times closer to the x-axis than they used to be. All right, now we're going to take a look at what happens instead of multiplying the entire function by a number. Now let's look at just multiplying our input values or our x values. So let's go back to our function here, and let's have it be b for this. So let's just start with 1 to 10. And if we adjust the value of b, let's see what happens. Well, this time, notice the larger that b is, the more pressing towards the y-axis that we get. So we don't have it going towards the x-axis anymore. We have it going towards the y-axis. So for values of b that are bigger than 1, it's a horizontal compression. So the higher that value of b is, the bigger the number we're multiplying our inputs by, the more of a compression we get. So it presses it inward towards the y-axis. If we look at what happens here, the factor is b. So now we're, in this case, we are, we'll go to a nice neat number, 5. We're 5 times closer to the y-axis than we used to be. So the bigger the value of b, the more of a factor we have. It's a horizontal compression by that value of b. The x-coordinates, again, are now b times closer to the y-axis. Let's see what happens if we multiply by between 0 and 1. So we'll set the values of b to be between 0 and 1. And now let's see what happens if we multiply our inputs by a number that gets closer to 0. So as you might have suspected, the graph now is stretching. So here, if we do, let's look at 0.25, if I can get that. Here we have stretched out, like with a slinky that gets stretched out and is no longer good. So now our point is going to be much further away from the y-axis than it used to be. It's not very, for right now, it's not very feasible to have all these radians here. So, but if b is between 0 and 1, it's a horizontal stretch. And once again, if your value is between 0 and 1, we take the reciprocal of that value for the factor. So vertical compressions and horizontal stretches, we take the reciprocal of that value to get the factor. And now it's that many times further away. Actually, this should be the reciprocal here, 1 over b that many times. So they're further away now from the y-axis than they used to be. All right, example 5, determine the graph of f of x equals sine of x. For each, we have sine of 12x. Well, 12 is bigger than 1, and it's going to be a horizontal compression by a factor of 12. All right, next up we have g of x equals sine of 1/5 x. The 1/5 is between 0 and 1, so it is going to be a horizontal stretch. And we take the reciprocal of 1/5 to get the factor, which in this case is 5. So now all your points are 5 times further away from the y-axis than they used to be. All right, that about does it for this video. Thanks for watching, and I'll see you.